I want to introduce our third speaker, Dr. Millie Chapman. She's an assistant professor of environmental policy at ETH. Her research is at the intersection of decision science, ecology, and data justice, really turning ecological science to practical policy solutions. So I'd like you to give a warm welcome to Millie.
So I'm going to talk today a little bit about how AI can help inform just environmental futures. As we were already told, I'm Millie. I'm a new assistant professor at ETH. So of course, everyone in this room knows we're in the midst of multiple intertwined global environmental crises. And I'd like to start my talk actually with these global warming stripes and an analogous representation of biodiversity loss over the same 50-year time horizon, partially because they've been incredibly influential at kind of motivating policy and motivating the public around both of these crises. But of course, they're vast oversimplifications of what are really spatially heterogeneous and complex, both drivers and impacts of these crises. And while the crises themselves and kind of their biophysical impacts are quite spatially complex, so are the policies that are being put into place to mitigate those impacts and address those drivers. Of course, we have global conventions like the UNFCCC and the Convention on Biological Diversity, but ultimately these international agreements are being implemented by national, subnational, and even local scale governments. And so what my work really thinks about is how and where AI, or more broadly, computational tools, can help inform robust and equitable strategies to meet biodiversity and climate targets, and when and why we should use caution. Really thinking about how we can use AI not only to understand ecosystems like we've learned about this morning, but combine those insights with decision science and ethics and justice to go from these ecosystem insights to decision strategies for implementing these multilateral policies. And a lot of my ongoing work is really focused on global biodiversity policy. So in 2022, the Convention on Biological Diversity signed the Global Biodiversity Framework, which outlines a whole bunch of global targets, some of which are very charismatic. A lot of people have probably heard of 30 by 30, which is this global target to protect 30% of landscapes by 2030. But there's also targets within this framework around restoring 30% of global landscapes, as well as doing this all kind of in an inclusive and strategically planned way. And so that's what I'm going to talk a little bit about today, is how we come up with these strategies for implementing these policies and understanding their potential impacts. So one of the challenges here is that we often plan for kind of different policies naive to the other policy targets that are being put into place. So we have a lot of global scale, national scale, local scale conservation targets, and we can come up with priorities for where we might invest in those actions to have the best outcomes for biodiversity, leveraging a lot of the data that we learned about this morning about where species are and how different land management actions might impact those species distributions. But we also have restoration targets, and we have a lot of production demands on our landscape. And so a lot of my work is thinking about how we can plan all of these in concert with one another, really thinking about the ways in which they interact with each other and coming up with more holistic strategies for planning land and planning the implementation of these policies. And yeah, so kind of a lot of the computational work in this policy design space really focuses on devising strategies, spatial strategies specifically. And of course, we can kind of think about this as an optimization problem. How might we optimally allocate our landscape to restoration, conservation, production? But that is a really value-driven question. And so we're often thinking about it under a range of scenarios. How much do we care about climate mitigation on the landscape versus biodiversity conservation? How exactly might these policies be implemented? How do we think about international cooperation, which is what a lot of my work focuses on? And how might production demands change in different scenarios of the future? And so we can come up with cool maps about what 2030 landscapes might look like across these different land management measures and better understand the outcomes of these policies, both in terms of their carbon benefits, but also their biodiversity benefits. So where does AI come into all of this? Actually, kind of the decision strategy design in a lot of these contexts, and especially historically, has relied pretty much exclusively on kind of traditional optimization approaches. That said, a lot of the underlying data that goes into these strategy designs are derived from kind of deep learning methods. We learned a lot about biodiversity distributions, and a lot of those methods kind of feed into these models. Also, how do we think about carbon benefits? We're often having to estimate land-based carbon sequestration, both kind of the current landscape, but also how that might change under different land management measures. So what happens when we restore a degraded agricultural landscape into a native grassland or something like this? Also, kind of how we project production demands. I think there's a lot of applications of AI and emerging computational tools to that part of the problem. But there's also, I think, a lot of applications of AI and emerging computational tools to the strategy design itself. A lot of my ongoing work is thinking about how we can move from going from just like current landscape to some 2030 landscape, and rather think about these as sequential and adaptive decisions that happen over these decadal policy horizons. So ultimately, we're trying to meet 2030 targets, 2050 targets, but that's not happening in some single static decision. Of course, that's happening over the course of many years, and ideally with updated information about the ways in which the world is changing, as well as just kind of more information about the world itself. So we can ask not only where, but in what order. And I won't go into kind of some of the methods that we're thinking about in this space, but a lot of people are proposing things like reinforcement learning to help kind of come up with more complex decisions that are both spatial and sequential. Of course, though, a lot of these algorithms have been designed in the context of tools, simple robotics tasks, and otherwise, and now we're proposing to use them to monitor our ecosystems, manipulate our ecosystems, inform our decisions, and even enforce our environmental policies. What could possibly go wrong? If the rest of the world has anything to say about it, actually a fair bit. So a lot of what my lab focuses on is how we understand the ways in which these algorithmic tools might shift power dynamics and accountability when applied to problems of environmental policy. But it's not only about kind of the algorithms themselves and the ways in which they shift who has power in environmental decision-making, but also, as we've heard about time and time again, the underlying data that goes into these models. So when we look at the biodiversity data that underlies the species distribution models, that underlie the sort of decision problems that I work on, we see not what we know about species distributions. Earlier, when we asked, like, where are species, someone yelled out, in the tropics. This is a map of the Global Biodiversity Information Facility, which is kind of the biggest global repository of biodiversity data. It has about 3 billion observations, a bit more probably by now. Anyways, not in the tropics, as we can see. Rather, this is really kind of a map of macroeconomic patterns. We can see that we have a lot more observations in high-income countries. But if we look at one of these high-income countries, the United States, which is where I'm from, we can see additional biases, cities, roads. And if we look at one of these cities, Los Angeles, we can see the legacy effects of racist policies. We have almost double the amount of biodiversity information in neighborhoods that were not historically segregated. We can see armed conflict and colonialism and when, where, and by whom these data are collected, which hopefully leaves us all with the question and a continued discussion around how these social, political, and historic dimensions of our data propagate through the ecological insights we derive from these data via the models that they are informing, and the distributional equity of the decision strategies for policy implementation that we come up with. And hopefully, more positively, what we can do about it. Of course, we can try to correct for biases, understand how they change our ecological insights and might change our decision strategies. But there's a number of problems with that, maybe the most pronounced of which is that people, our politics, our economies, and our histories are major drivers of ecosystem composition, which means disentangling the observer from the observed is not actually an easy task, which I think we've heard, again, time and time again, that actually understanding these biases is a hard problem. And this is something we talk about in a recent paper really thinking about how we can combine sort of global scale data repositories with local scale context, and think about data as social infrastructure and algorithms as well as social infrastructure and as, yeah. And so maybe the question isn't actually, at the end of the day, can AI help inform just environmental futures, but how and where it might help inform strategies and when and why we should use caution. And with that, thanks again for the patience.